Good morning, everyone, and welcome to the webinar today. My name is Carrie Berger, and I'm the coordinator of the Northwest Fire Science Consortium. The consortium is a regional program for fire science delivery in the Northwest, and we are part of a national network of fire science exchanges that are hosted by the Joint Fire Science Program. So we strive to offer diversity of opportunities for people to participate in, and hosting webinars is just one way that we accomplish that. So you're listening today to the final webinar in our fall webinar series on communication and fire. I have muted your audio to avoid any noise interference, so if you have a question, please type that into the chat box. I'd like to welcome with us today John Saltenberger. John is a meteorologist with the U.S. Fish and Wildlife Service and has spent 17 seasons as an incident meteorologist, working in the field on deployment with firefighting teams across the U.S. So John, thank you for being with us today, and you can go ahead when you're ready.
Okay, very well. Thank you, Carrie. I'm going to advance the slide here up to, there we go, my title slide. I'm John Saltenberger, U.S. Fish and Wildlife Service in DOI. I'm trained as a meteorologist, and as Carrie pointed out, I have experience in working with just about all aspects of meteorological support for fire management, including deployment as an incident meteorologist on fire management teams across the U.S. I've also traveled internationally in fire projects to Canada and twice to Australia. I work now at the Northwest Interagency Coordination Center in Portland. I'm going to advance my slide here. I'll try to advance the slide. Not working at this point. Okay, now I think I can advance that slide. There we go. All right, so, oops, I'll back up one frame. Okay, there we go. You should see a map of the National Incident Coordination System. I work at the Northwest Coordination Center, which is a part of a chain of regional interagency coordination centers across the U.S., including Alaska and Hawaii. Northwest Coordination Center is located in downtown Portland. We're an interagency center whose responsibilities include distribution of firefighting resources, fire management resources during the shoulder seasons and primarily during wildfire season in the Pacific Northwest. Our specific job responsibilities here at NWC are all aspects of incident workload for federal and state agencies across Oregon and Washington. That includes daily status reporting of the distribution and usage and commitment of firefighting resources and fire management resources. We're also responsible for mobilizing firefighting resources in the event of large, costly type fires, including their logistical support. And we also do planning here, which includes prioritizing and in some cases pre-positioning firefighting resources in anticipation of outbreaks of large, costly fires rather than simply reacting to them. So we're trying to take a proactive stance. As such, the 3 to 5 day planning window is crucial for ordering and activation and support for fire management resources across the Pacific Northwest. And that's where my job comes in. As a meteorologist, I'm daily tracking weather patterns and fire danger across the Pacific Northwest, as well as other geographic areas across the U.S., and anticipating those conditions under which our workload is likely to change, either upwards or downwards. We're primarily concerned in upwards fluctuations in fire potential, as fire danger waxes and wanes and conducive weather patterns change in association with ignition sources. When we see optimum combinations of fire danger, fire weather, and ignition sources, then we know that there's a great likelihood of new large, costly type fires that are going to result in NWC getting involved in mobilizing and supporting extensive fire management resources, both from within the region and from without when the conditions warrant. As I say, that 3 to 5 day planning window is crucial, and as a meteorologist, I'm constantly looking at weather pattern changes and fire danger changes in that 3 to 5 day window so that the center managers here can make more informed decisions about distribution of firefighting resources. Okay, so let's take a look at a number of metrics of measuring what was the severity of wildland fires in the last decade, both in terms of numbers of fires reported and the acreage burned. On the graph here in front of us, we have the numbers of fires reported since the year 2000 for both Oregon and Washington, the Northwest geographic area, since 2000. And in terms of the number of fires reported each year, it varies between 3,000 and 5,000 from year to year. There's not a heck of a lot of variation from year to year, as you can see. The 17-year average for the geographic area is just over 4,000 fires in a typical year. And you can see that we had a few years that were pretty close to average, but by and large we're either varying upwards or downwards above that. But I think it's fair to say that we're generally between 3,000 and 5,000 fires reported each year for the geographic area during a fire season. In 2016, what we had burn across the geographic area, let's see if I can make that come up. There we go. 2016, we reported so far, and our total isn't complete yet, but our preliminary total for the 2016 fire season is 2,400 fires. Looks like it's about 60% of normal at this point. So we had a relatively slow year in terms of the numbers of fires, according to our preliminary statistics. Let's bump forward one more slide, and now we're looking at a different metric, the total acres burned by year since 2000 for the same area in Oregon and Washington. And as you can see, there's a lot more variation from year to year in number of acres burned as opposed to the number of fires that were reported. As you can see, we had a number of years that were very low, and we had a number of years that were very high. And so it's almost pointless to calculate an average from that, but if we did, the 17-year average is 641,000 plus acres in an average year. Although you can see, I think there was only one year that was anywhere close to average. That was 2001. It seems like in terms of the number of acres burned each year, it's either well above average or it's well below average. Either the button seems to be turned on or it seems to be turned off in terms of the acreage burned from year to year. Of course, that includes both rangelands and timber-type fires. For 2016, we burned just shy of 500,000 acres to 499,000 acres, which is just a little bit below average for us. So in terms of characterizing how a fire season progresses, we can look at the total number of acres burned, the numbers of fires reported, and they vary from year to year, as we pointed out. It's illustrative to look at the tracking of fire danger for the geographic area as a whole or individual sub-reporting areas, which we use. There's 12 of them that we use in the Pacific Northwest. And on a daily basis, we're constantly looking at the current and anticipated fire danger because it has such a hand in determining what our likely fire workload is likely to be over the next few days or even the next few weeks. So tracking daily fire danger in terms of what we've seen and where we're likely to go is a big part of my daily job. So we do that here in the Pacific Northwest on an interagency region-wide basis by just subdividing the region up into 12 different reporting areas that we call predictive service areas, and doing an iterative study of the number of fire danger reporting stations across the region. We use 73 key fire danger reporting stations on a daily basis to feed into our fire potential model for tracking of where we've been in terms of fire danger across the region and where we're likely to go over the next 7 to 10 days or so. And we reinitialize that model each day with the current reports from fire danger as they come to us each morning. We're going to be looking at pretty much an average of all these contributing reporting stations to characterize fire danger fluctuations for the region as a whole for the 2016 season. Okay, so taking an average of fire danger index values from all of those reporting stations, we're using energy release component here from the National Fire Danger Rating System, energy release component for fuel model G, which is what we use to characterize fire danger for across the entire geographic area. And if we looked at what the typical variation in energy release component is during a typical fire season, at least averaging out all the seasons I have in my database, We start down in early June with fire danger index values at low values, and then there's a steady rise with some fluctuations right up to about the first week of August or so, and then it kind of holds steady through August with some fluctuations, and then we typically see a decline, again with some fluctuations through September, and it begins to tail off in October. Our typical tracking season, though, that we use here at NWC begins on June 1st, and we go right through the end of September, usually reaching that historical peak somewhere in the first week of August. And you can see it's kind of debatable. There's a lot of fluctuation from year to year and where that peak fire danger is in terms of energy release component, but it's typically right in that first week of August or so when we reach our historical average fire danger, peak average fire danger. Okay, so let's kind of keep in our mind's eye that variation in that fire danger index curve, the ERC curve that we would see in an average fire season across the geographic area. And I'm going to bump forward here and look at that average value plus the upwards or downwards variations of one or standard deviation above or below average in terms of ERC, and then the max values that we can see in those gray lines that we see traced in there. The red trace that we see overlaid on there is what actually happened during the 2016 fire season. So in essence, what I've done is use the red curve to illustrate what happened in 2016 versus what typically happens or what happens during an average fire season across the entire geographic area, averaging out energy release component values from all those 73 key reporting stations. And as you can see by looking at that red curve, that there are upwards or downwards fluctuations that happened in fire danger during any given fire season. If we look closely here, you can see that there's about 5 or 6 peak periods of fire danger interspersed with about 4 or 5 minimum periods of fire danger. You can easily see that the overall trend is upwards up to about August, and then there's a gradual downward trend. But within any given month during fire season, we have those upwards or downward trends in fire danger. And it's important to note those upwards or downward trends are really important on a small scale because it's typically during those upward trends and right at the peak of fire danger in one of the localized upward trends when our largest and most costly fires tend to break out. Okay, so let's see if we can break this down into more bite-sized chunks and look at those relative minimums and maximums that occurred during the 2016 fire season. As you can see with my arrows, I've pointed out a number of key maximums, localized maximums that occurred during the 2016 fire season. It's important to note those relative mins and maxes overlaid within the overall change within a fire season. So let's look at each month and the contributing contributions of each of those mins and maxes during each month of the fire season and what happened in the geographic area in terms of the outbreaks of large and costly type fires. Okay, so we'll look first at those fluctuations upwards or downwards as they occur on those relative mins and maxes during each month. They're strongly related to what the weather has been. When we get into ridging type patterns in the atmosphere, meteorologists love to look at their weather charts, especially the 500 millibar chart, which you may or may not have heard mention of. That's what we see in the left frame here. It's a ridge type pattern with what we call high heights, strong high pressure across the Intermountain West, and we're leading to warm weather and an upward fluctuation in fire danger due to the hot, dry weather that's experienced. The opposite occurs when we get into troughing type patterns, which is what we see in the right frame. The trough type pattern is just the opposite. We get into lower heights, cooler weather, rain showers or actual rain, and much higher humidity with trough type patterns across the Pacific Northwest. It's important to watch the variation from ridges to troughs across the globe because as we look at that animation in the right frame, you can see that the ridge trough pattern is varying over the Pacific Northwest as those ridges and troughs move in a wave train across the entire northern hemisphere. Patterns over North America becomes patterns over the Atlantic, which become patterns over Europe, and which become patterns over Asia, and then returning to the Pacific. If we can look at the variation of those ridges and troughs on a daily basis, we have a big clue as to how fire danger will vary from day to day and the likelihood of large, costly type fires The left frame that we can see here shows the variation in 500 millibar patterns at any one spot, and where large fires are likely to break out, according to a study that was done in development of the Haines Index and other atmospheric indices. Typically, large, costly fires break out when a trough is moving through, which is what that left frame is trying to illustrate to us. There's a strong relationship between the ridge-trough pattern and the jet stream and outbreaks of large, costly fires. Going back and looking at history shows that there are observable and repeatable patterns in the jet stream that really give us a feel for how fire danger will fluctuate and the likelihood of outbreaks of large, costly type fires. And it's those ridge-trough patterns in the jet stream that we see in the animation that give rise to those changes in fire danger that we see during any given month across the geographic area. All right, so the evolution of fire season 2016, I'll start off with June, just looking at the June fluctuations in average fire danger across the region. And as you can see, we definitely went through a ridge-trough pattern with fire danger in association with ridging and troughing in the upper atmosphere. We look closely at the first ridge that occurred with some hot, dry weather in that first week of June, peaking right around June 7th with a peak in fire danger across the geographic area. That's when we saw the outbreaks of 3 large, costly type fires across the geographic area, starting with the Draw Fire, the Acquawanda Fire in Central Oregon, and the Hawaii Canyon Fire in southeastern Oregon. These turned into large, costly type fires that occurred early in the season. And because of the drought conditions that we saw, we had serious fire behavior showing up in early June and set everybody on edge, beginning with the potential severity. Costs associated with those 3 fires alone were for almost $5 million. Now you can see the second half of June was followed by a cooling trend with a downward trend in fire danger, returning right back to about normal again before a next upward trend began in late June and early July. That's the kind of variation that we watch for, and we typically find that those large, costly fires break out right at the peak of fire danger. Okay, so I'll look at July now at this point. You can see the overall trend in fire danger was headed upwards, but we did have that ridge-trough variation during July as well. If we look at the first part of July, right around July 5th, we capped a warming, drying trend right around the 4th of July weekend, July 5th, before the next plunge in fire danger occurred. And right around that July 4th, 5th weekend, again, we started seeing large, costly type fires. In this case, it was the Rocky Ford type fire that happened. Costs associated with Rocky Ford, $400,000 plus. Immediately after the 4th of July weekend, across the geographic area, we saw one of those upper air troughs move in and take station over Oregon and Washington through much of the remainder of July. As you can see, fire danger actually plunged below average, hovered near average, and then started rising above average by the end of July at that point. But the fact that we had that cooler, moisture weather associated with the superposition of an upper-level trough over the geographic area largely suppressed fire activity. As you can see, we really only got one serious large, costly fire during July. Let's look at what happened during August. So we move forward into August now, so we can see August began with fire danger above average at a relative minimum about the 10th of August, and then really shot up above average for the second half of August, going just about to peak record values in the second half of August. Now, it's during that first peak in fire danger, right around July 28th to August 7th, we saw a series of outbreaks of large, costly type fires in Oregon and Washington, including the Range 12 fire, which wound up being the largest fire of the year for the geographic area, the Rail fire, which probably was the most costly fire of the geographic area for the fire season 2016, as well as a number of other fires, high-profile fires, such as the Kewah fire and the Bybee Creek fire at Crater Lake National Park, all of which wound up being costly fires for the geographic area. We wound up spending $45 million in suppression of these 6 fires and other smaller ones going on at that same time. So that peak in fire danger early in August, July 28th to August 7th, that was a serious peak that was broken down when the ridge-trough pattern changed, and we saw some winds, we saw some instability, and we saw some lightning associated with the change from ridges to troughs. Okay, let's look at the second peak in August. Fire danger decreased temporarily, bringing it just back down to close to average, and then shot back up again for the second half of August, reaching another peak again, August 21 to 26. Another serious peak in fire danger, in fact, actually reaching record values of around the 20th of August or so. And at that point, we saw outbreaks of more large, costly fires, mainly in Washington in this case, Cayuse, Spokane, and Cherry Road, the Deep North Heart, and the 2500 Road fires breaking out during that secondary peak in August, totaling near $20 million of suppression costs, and that's associated with that secondary peak. Finally, we take a look at some of the normalized fire danger index values right as we hit our peak fire danger index values around August 26th or so. Again, these are the ERC values for Fuel Model G for all the reporting stations that we use in Oregon and Washington. And we're looking at values, near record values, particularly west of the Cascades, which had undergone relatively drier weather than east of the Cascades had at that point. So in terms of absolute values, the ERC values aren't as high on the west side as they are on the east side, but they are at record values for the reporting zones on the west side. So that's about the time we hit our peak fire danger index values, was in that third week of August. Okay, so moving forward here for September, we saw a first peak in the middle of September, September 10th through 16th in fire danger index values. And as you can see, for the month as a whole, fire danger was above average for just about the entire month in September. Even though we were on a downswing, it was drier than typical right through September. And during that first fire danger peak in September, we saw the outbreak of the Rock Creek Fire, the High Pass Fire, and the Elmer City Fire in Washington. Suppression cost $13.5 million for that secondary peak there in September, even though we were on a relative downswing. Okay, let's talk about lightning and wildfire facts for Oregon and Washington. It's important to note at this point. First, if we look at the breakdown of all wildfires that happen in Oregon and Washington, about 46% of the total are ignited by lightning. The other 54% are human-caused. Overall, it's about a half-and-half split between lightning-caused fires and human-caused fires in the Pacific Northwest, Oregon and Washington. Here's an interesting statistic. Initial attack forces have an excellent record of keeping human-caused fires small, even on dry, windy, and unstable days. That initial attack forces across the Pacific Northwest have something like a 97 or 98% success record in initial attack on human-caused fires, even on dry, windy, unstable days. They're extraordinarily good at stopping fires before they become large, costly type fires. It's interesting to note that of the fires that do become large in the Pacific Northwest, about 3/4 of them are caused by lightning. So that the main concern for us for outbreaks of large, costly fires is to a smaller extent from human-caused fires, to a much larger extent from lightning-caused fires, simply because lightning can happen anywhere, and ignitions can happen from lightning in the high country or inaccessible terrain that takes firefighters a lot longer time to get there, and they're dealing with denser fuels and more difficult access. Therefore, it's likely that large fires are more likely caused from lightning, simply because it takes more time to get to them, and they have more time to get large. Let's look at lightning statistics for those same 17 fire seasons, June, July, August, September, across the Pacific Northwest. Lightning strike counts from year to year for each fire season. We track that on a daily basis and sum them up at the end of the year. And as you can see, the 17-year average is pretty close to about 80,000 strikes in an average year, although we've had very few average years. It seems to be either above average or below average with lightning strike counts. But the 17-year average just shy of 80,000 strikes. You can see we had a big year in 2013. We wound up with 249,000 strikes. It was just an immense year for lightning across the Pacific Northwest. And the lowest year was 25,000 strikes in 2000. When we actually summed up for 2016, the number of strikes, it even was lower than 2,000. It wound up being only 22,000 plus strikes for the geographic area for the 2016 season, which means that's only 28% of the number of lightning strikes occurred during the 2016 season, as opposed to that 17-year running average of almost 80,000 strikes in a typical year. So we definitely were below average in terms of the number of lightning strikes, which certainly lends support to the fact that we had a below average number of fires across the geographic area and a below average number of acres burned for the geographic area as well for the 2016 season. The number of days that lightning occurred was 63 days that we actually recorded lightning. The normal number of days that lightning occur was 48 over the Pacific Northwest, which is to say that we had a greater number of days with lightning, but a lesser number of overall strikes. In other words, series of generally weak thunderstorms coming across the geographic area. Now, the biggest event of the 2016 season was June 5th, 6th, right in the early part of the season. We wound up having a 24-hour strike count of just over 2,200 strikes, mainly concentrated in southern Oregon and along the crest of the Cascades in the June 5th, 6th 24-hour period. All right, so now it's interesting to look at the lightning strike count overlaid with our yearly fluctuations in fire danger. So here in the red, we see our month-to-month variations in fire danger, and as we can see, most of the 2016 season, we were above average fire danger for the entire geographic area, with just some variations, some exceptions to that during July. Now, if we overlay the lightning strike count on a daily basis with our fluctuations in fire danger, you can see most of the lightning, weak though it was, happened early in the season, with the biggest amounts actually occurring in June, which is unusual for us in early June. Usually our peak lightning occurs in July and August. But as you can see, if you can kind of just blur your eyes a little bit and look at that, we actually had a downward trend in lightning day-to-day from June right through the middle of August or so. In fact, if you look closely at this thing, you can see that about the time we were having our maximum fire danger in late August, we were at a minimum from lightning strike counts. So we went through that period of very dry conditions, but really not much of an ignition source from lightning. It was mainly human-caused fires that caused so much problem for us during the 2016 season. I think we dodged a bullet in this case, because if we'd had normal amounts of lightning during that peak period of fire danger in late August, we might have had a completely different fire season, maybe one rivaling the 2015 season. But it didn't come to pass. Most of our lightning occurred early in the season when fire danger was relatively low. Okay, so that big gap, August 10th through September 7th, lots of fire danger, but not much lightning strike. Okay, so to summarize the 2016 season, 2,400 reported fires for Oregon and Washington according to our preliminary count. 67 fires of those 2,400 met large size criteria, and that varies from reporting area to reporting area. We had mobilizations of 17 Type 1 or Type 2 incident management teams, 22,000 lightning strikes up to October 1st. The largest fire from Washington during the season was the Range 12 fire at 176,600 acres. Oregon's largest fire, and probably the longest lasting fire that I've seen in the last few years, was the Rail fire for 41,700 acres. Overall, it looks like we spent about $104 million, and at peak fire activity, we had 4,200 wildland firefighters at work in the geographic area during the 2016 season. And that is the sum total of my presentation. I think I'm bringing in right around a half an hour, so I'm open to questions at this point for the values that I have been able to present to us today.
Well, thank you so much for that summary, John. That was really interesting. And like you said, let's go ahead and open it up for questions. Let me get my chat box open here. And so from Jacqueline, would you please send the recording to her? For some reason, unfortunately, she had no sound. Thank you. Well, I'll go ahead and send her the recording of this webinar.
Certainly. And I'm also happy to send a copy of this PowerPoint presentation to anybody who wants it. I'll just have Carrie forward the requests or I'll send the, well, Carrie has a copy of the PowerPoint presentation.
I do, yeah.
Yeah, feel free to send that out to anybody who requests it.
Okay, thank you for that. Great. Any other questions? We'll just give a couple minutes here, and while we're waiting,
Sure.
Again, I just want to thank you, John, for taking time out of your busy schedule, and I can see snow starting to fall here in Corvallis, and I can imagine you're getting some of that in Portland. So, and I wanted to also thank everybody else for taking time out of their schedules to tune in today, and also throughout this fall webinar series on communication and fire. It's been an excellent series, and if anybody ever has an interesting idea for a webinar or wants to hear something brought up, just please feel free to contact either myself at carrie.berger@oregonstate.edu or Janine Creighton, who's our administrative director. She can also be contacted through Oregon State University.
Yeah, Carrie, I'll be the first to offer up there. I can do additional presentations looking at fluctuations in fire danger and their relationship to weather patterns and ignition sources. I could easily put together another half-hour presentation very similar to this one for a future slot on your agenda.
Excellent. I really appreciate that. Okay, so I don't see any. Oh.
Yeah, I see one question from David Shaw. So the question is, does lightning occur in certain regions more than others, like Southwest Oregon area? And the answer to that question is Southeast Oregon undergoes the most lightning. We break into 12 different rating areas, and we sum up the number of strikes in each rating area. And just about every year, it's that Southeastern Oregon, South Central Oregon that gets the most lightning on a year-by-year basis. It varies from year to year, but overall the winter and lightning strike counts tends to be Southeast Oregon. It's exposed to a lot of heat. It's exposed to upper-level moisture, what we call the monsoon, and it's also a big reporting area, so it does gather a lot of strikes. Interestingly enough, we have found by threading through the lightning statistics and versus fire outbreaks in southeastern Oregon is that it takes a lot of lightning in southeast Oregon, like high-end thunderstorms, high-end strike counts, to really boost the potential for new large fires in southeastern Oregon. Because the terrain is relatively flat and there's a lot of fire crews out there and they're good at their jobs, those fire crews tend to stop fires from humans or even from weak lightning storms something like 98% of the time. It's just those few thunderstorms that come with a lot of strikes that can overwhelm them. And it's relatively rare to get large, costly fires from lightning unless there is a lot of lightning out there in southeast Oregon. Southwest Oregon is a different animal. They don't get as many lightning strikes out there in the typical year, but it's also more problematic because the terrain is very convoluted, very steep terrain, lots of vegetation, lots of trees. And when we do get lightning, concentrated lightning in southwest Oregon, while it's not the #1 lightning zone, it does have big problems from fire starts, particularly when we get lots of fire starts from lightning in a short period of time. Simply put, the number of new fire starts that can happen from a severe thunderstorm in a 24-hour period overwhelms the ability of initial attack firefighters to find and suppress those fires before they get large and costly. So yeah, each reporting area, and we use 12 of them, has its different characteristic response to fluctuations in fire danger and lightning, and that's essentially the meat of the research that we do at the center in the off season, to see if we can better suss out the relationships between fire starts, large costly fire outbreaks, and lightning and weather.
Mm-hmm. Good. I have a message here that says, just a quick reminder, the information on costs that John shared were for suppression costs only. These do not include resource value loss or improvement structure cost loss. And that's
Correct.
An important point. Yeah.
Yeah.
And then just a compliment to you, John, I got a message that said that this was awesome, very nice.
Well, I'm happy to help. This is an interesting topic. It keeps me engaged from year to year. One of our research areas going on right now is to see if we can leverage new technology to forecast those peaks and troughs in fire danger during a given month. There's new tools coming online that I hope to be able to try to leverage to see if we can look weeks ahead of time to identify those peaks and troughs, because they're so important to anticipating large, costly fire outbreaks. I don't know if the new tools will prove worthwhile or not, but I am certainly going to explore them to see if they can be leveraged to give us better forewarning.
Absolutely. I have another message here. How often does an IMT consult with you on the decision to suppress versus fire use?
Yeah, now that's done by the host unit, and they have fire management plans. BLM, Forest Service, parks, and refuges all have fire management plans worked out in advance, that when fires occur in certain areas, their decision is usually pre-made as to whether that's a suppress or other management for that fire. So by the time an incident management team is ordered, that's usually an indication that the decision has already been made to suppress. So it's fairly rare when I get a direct query from an incident management team here, at least in the first stages of fire outbreaks.
Okay, thank you. Any other questions? I'm not seeing any on my end. John, are you seeing any questions to you privately on your end?
Nothing new at this point.
Okay. Okay, if nothing else is coming in, again, thank you to everybody for this great webinar, for joining in, and John for speaking with us today. That was really interesting. With that, I guess we'll close here so that, John, if you need to, you can get back on the road. I don't know if it's snowing up there in Portland yet, or...
not quite yet.
Yeah, so we're probably the first wave of it. I think I saw it coming up north towards you. So well, stay safe, everybody, and happy holiday season to y'all. Thank you.
Very good. Thanks, Carrie.
Thank you.
Bye-bye.